So, hello everyone, welcome to the European Non-Associative Algebra Seminar. The speaker of today is Kenji Iohara. He will speak on elliptic root systems. Please.
Thank you very much for invitation. And so today I'm going to speak about, say, so-called elliptic root systems. So let me just define these. What are they and what we can do and why we are interested in such objects. So, so first I'm going to talk about, say, slightly generalized root systems and the marking of what is so-called marking of a root system. So what do we look at it? So we take a finite dimensional vector space R. Of course, we can think of the infinite dimensional case, but this is not of our concern. And a symmetric bilinear form with signature L plus for the plus positive part and L0 for the eigenvalue 0 part and L minus for the negative part. And then for a vector with non-zero length, we define this dual root alpha check by this formula, which is sometimes called co-root, but here we call it dual root. And the W alpha, so this is a reflection, as you know. Well, this is somehow Saito in 1955. He introduced such kind of things. So generalized root system belonging to this vector space with this fixed metric, verifying these 5 conditions. So if you look at it, the first one is just the usual classical things, and the third one is also the classical, and the fourth one is also classical. So up to this part, it's okay. And the fifth is sort of irreducibility. And the second one, here we exclude isotropic roots, because in some sense, the set of isotropic roots are out of control with respect to this sort of notion, in particular the action of the while group and so forth. It doesn't work that well. So, so we sort of say generalize this real root systems in a sense. So it should be called probably generalized real root system, and I don't know, but here we call it in this way. So as an example, let me think about the case where this form is positive semi-definite, so with the signature L and 0. Of course, for n equals to 0, this is a finite root system, and n equals to 1, this is affine root systems. Well, for affine root system, there's a little bit of some bizarre, in a sense that Katz and Moody at the same time, so they independently use the notions which is somehow similar but a bit different. And MacDonald in 72, he used another symbol, and Kenji Saito used again another symbol, and Carter also used another symbol. So here is this 5 list symbols, which are more or less used by several persons. So you may see here for the ADE case, it's okay. For the so-called the twisted case here, for the DL plus 1, 2, BL2 and a BL check and a BL2, but with the 2 parentheses here and the BL tilde T, well, it might be too much, but we have these symbols. And for the twisted case, here is another one here. If you see this A2L2 and AL2 and BCL and BCL2 and CL tilde prime, it's really a bazaar. So you may choose whatever you like, but here we may choose what Saito proposed, and it reflects some sort of, say, structure of the root systems. well, if you look at the non-reduced case, there's this 4 types, which is only named by MacDonald, and we keep this convention. Let me just recall. So what are they in the affine case? So this XL1 in Saito sense or cut sense is the same. Here we have this things, the typical one. And for this number to be 2 or 3, there's slight difference. We have to shift a little bit here, depending on the number here. So if R is 1, it's of these types. I mean the first type, and if R is not 1, it's a little bit new. It's sort of, say, twisted case. And BCL2, which cuts code A2L2, is of this type. So here you have 3 lengths. By the way, this B is an element of the radical. So basically you have 3 lengths here, 2 lengths here, and only 1 length. For the non-reduced case, so this is this is by MacDonald, so you can see his famous paper about the MacDonald identity. Here you have 4 such types. Just a small remark. Here, this is a really classical one, and here, the C-check B series, because of this non-reduced nature, we have 4 here and a 1. And in between, you have 1 here and a 2 there, and in the middle, it's slightly different. So in total, we have 4 types. What is funny here is, in fact, all these affine reduced root systems are realized as a root system of a Lie algebra. In the non-reduced case, they correspond to the Lie superalgebra, for which the universal enveloping algebra is integral domain. So this is very special feature. Wait a moment. I have some problem. So now the question is, what can we do with the elliptic root system? So elliptic root system is the case with when n equals to 2. This means you have 2-dimensional radical, and this 2-dimensional radical in some geometric image, something corresponds to the first homology of the elliptic curve or torus. So this somehow comes from the geometry, but when we think of the classification, this is not so simple exercises. Well, this Kenji Saito introduced a way, so the notion called marking, which is the subspace of the radical of I. Of course, this is 2-dimensional here. And under the condition that you should have this condition, so you can't take 2 diagonal in a sense. But if you have this one and the G is of dimension 1, then it's quotient. I mean, the R is a subset of F, and you look at its image in the quotient, it becomes an affine root system. And in particular, if this is reduced type, then you can always find the affine root system inside R with this property. So now we assume that this is of dimension 1, always dimension 1, and identify these 2 things. Well, what Kenji did is, in fact, with the aid of the classification here in the quotient side, he may see how can we lift to the structure of the elliptic root systems. So, so for this, you take a, say, marked elliptic root systems where the quotient is reduced, and think of this quotient root system and realize it inside R, and take another generator of this, say, radical Zi, so from here, and write it as Za plus Zb. So remember that this B direction is in this affine part, and A is the newly added one. So for each affine part, you can somehow translate in the A direction, and this A direction should be calculated in the following manner. So you may take a positive integer, which is minimum among all such, say, integers, and I call it counting. So what is happy with this? In fact, for each affine root, alpha plus g intersection r is of this one, namely, root of such kind is always of multiple of k alpha, alpha translated by k alpha times a for several times. And in fact, the classification of this pair R of the root system and the marking becomes the same as the classification of the, say, this set of countings. So by this way, in some sense, it reduces the problems to the classification or the combinatorics of the affine root system in a sense. Well, he could handle the classification by that way and see that for ADE type case, as in affine case, you only have one type. So here, one signifies here it's 1 and 1. For the BCF type, you can have R1 and R2 to be 1 or 2. And for G2 type, you may have 1 or 3, and it looks like this. This seems to be a classical thing, and I think you may see what it is. Be careful that the position of R1 and R2 is somehow switched. So this is because of our choice. For this BCL type case, well, there's one type where you can just only add ZA, and the other one of these types, if you remember, it somehow resembles a C-check BCL type. And here, this is of type BBL check type or the C-check CL type. Okay, so this is what we can, so these are what we can imagine, but in fact, there's something very strange, which is we don't have full lattice of this radical part, but we have something with the parity conditions on the coefficients in this way. So, of course, A1 has only one, I mean, the real root of the A1 has only one length, so we don't have any choice and we could write it in that way. For the BL or the CL type, here you have the short root and the long root. For BL type, you have the star type part here as a short root. For CL, it's at the long root. In fact, this somehow reflects the fact that this class of root system is stable by taking the dual root. So once having a short root here, you may have the long root here, and
now the rabbit has a whole pile of chicken cut.
pardon? So now we go to the non-reduced case. Here, the non-reduced case is bit, well, in fact, by the same idea, we can classify it. It doesn't matter, we can do it. But it took about 70 pages long computations or 80 pages long computations, and it's not funny. And moreover, this we did it with Alice Fialowski and Saito, but this is another Saito. So if you wish, here I wrote the Chinese characters of the Saito here, And the other Saito also has another Chinese character, but they doesn't have the same character. So if you can distinguish, that's great enough, but you don't have to worry about it. They are at least different with this first name. Well, so by the way, this 70 pages long computations and 80 pages long computations for the classification is too risky. In fact, we repeated at least 10 times, and for 10 times we get the different results. So we said, okay, this is really bad idea. And then we tried another way, and finally we get something quite funny. And this is what I'm going to present a little bit. So let us write, since this is non-radius case, basically this is of BCL type. I may soon recall what is BCL for, just for you. So write this one with the union of the short root and the middle length root and the long root. And here, I may say, not really the positive part, but with the middle length union of these two, and then that one to the union of the first two. And in fact, it's somehow clear that in these guys, I mean the positive part or the bigger or the smaller part are respectively the B types or the C type marked elliptic root systems with the same G. And this somehow indicates that in fact we can use the results of Kyoji, I mean the classification of the reduced type, and this we know what are the type B, so to say type B marked elliptic root systems and the type C marked elliptic root systems. There's 5 of such types. If you wish, we can go back. So it's here. So from here, you may see that for the BC case, R1, R2 can be independently 1 or 2. So you have 4 types here. And then at the end, you have this star type case. So there's 5, each of them has 5 possibilities. So now we know that we just have to analyze these 25 cases to see from this what can we get. So what do? We just glue it. But gluing root system seems to be a little bit strange. It means, in fact, you first realize these two in the same ambient space Fi in such a way that the intersection gives you really the middle length part. I mean the same middle length part from both of these, which is of type DL11. Of course, for the rank 2 case, it's A1 times A1, and the rank 3 case, it's A3. By the way, for rank 1 case, there's no middle length part, so we have to treat it separately, but this is just a small affair. And after that, what do? We may take the automorphism of this root system, fixing this G, and then apply this rotation in a sense to this part. Recalling that this Rm is also a root system belonging to this Fi, so it's of the same type, and this automorphism is the linear automorphisms. I mean, restriction of the linear map. So you can apply also to that one, viewing this phi as a linear map or the endomorphism in F. And then it turns out that this guy becomes a root system. So what we have to do, if we know this automorphism group, we can in principle do it. But this is huge. In fact, it's an infinite group. But it's not a big problem, because if we take this phi, which comes from this B-type part, and calculate this root things, in fact, you may see that, well, this is by definition, and the phi s, in fact, is the automorphism of this one, so it doesn't change it, and you only have this phi. If you take phi L, the automorphism of the C-type part, and you compute these things, as this one is fixed by phi L, you can write it in this way, and you may see that this is phi M of this guy. So finally, we get this, this thing which says that multiplying automorphism of the B-type part, or this multiplying this automorphism of C-type from the left or from the right, it doesn't change it. So what we have to do is to see this double coset. You may probably say that, oh, this becomes more complicated than the original question, but in fact, it's not the case. These can be explicitly computed, and this becomes relatively small groups with a small set. By the way, this, of course, BCL is of such type, and where epsilon i's are orthonormal basis with respect to some metric, but so we carried out these computations and see for each representative, what does this give? Well, from 80 pages long computations, it's shortened to maximum 10 pages or 15 pages long computation. So we were happy with this one. And the result is, in fact, I said that we classify the non-reduced case, but this non-reduced case, to be precise, let me recall, is the quotient which is non-reduced. But it may happen that R itself is reduced, and indeed, here is the 4 cases, which, if you remember, is the one which you can obtain by flipping A and B from the known case by Kenji Saito. And if it's just only this one, well, there's nothing new. Fortunately, there was 2 other things, but in fact, these 2 other things, it's really not new, because it's in 2002, I think, Azam Said wrote a paper on this extended affine root system, and in particular for rank 2, he tried giving some classification. Under the condition R is reduced. And there we can see that he already found out this one, but he didn't name it, so we propose to call it in that way. Well, you may see somehow later this one. And if R itself is non-reduced, it's just a symbol, so you may say, okay, we don't understand anything and it's nothing. It doesn't talk anything, which I understand quite well. But let me just say a few words. So here you see this BCCL1 and the BCCL4, so it's sort of affinization. And this one and the 2 somehow is something parallel to the BCL type case in a reduced case, which is classified by Kenji. And for the star type case, here we have star 0 prime, star 1, and the star 1 prime also here, and a star S and a star L, and many crazy things. But it's more or less star type. You just have to see where this star type root systems appears. But there's one case which we call CHEX-CL2 diamond, which is neither of these 2 types. Let me just recall what are they briefly for some types of the root systems. So with those with 1, 0, or the 2i with I equals 1 or 2, and a 4 here, they are of this type. So if XL is of type BCL2, this was what you see in the Kenji's classification. And here we we also have it for these cases. So in total, here you have 4, here you have 4 types independently, so you have 16 root system coming from this kind of realization. Well, for the star type, it appears that in fact, if you remember the star type, I said that this star type things appears only in the short root part or the long root part for the reduced case. But here, what happens is, in fact, for something of type CHECK-CL2 with star I, with I0 or 1 or 1 prime, in particular, for I01, you may have the star type root systems here in a short root part and the long root part. Well, here you see it's only II. You can, of course, vary like the IJ. For some of them, they become isomorphic. And here you can also shift something, not only n, but n minus I prime and n minus j prime, and you can do it. But we can always translate it to this case. So somehow, if you have 2 of them, I mean the short one and the long one, which can be described in that way, you can fix one of them. So if you prefer, you can fix the long root part and in place of the short root part, and it doesn't matter. I mean, basically they give you these things. Well, as I said, the CHECK-CL2 diamond, very strange. Here, for the long root, short root, and the middle length root, it's of the classical type, but with the long root part, it's somehow diagonal. Well, so we thought that this guy is really particular and having something very strange. But in fact, let me say a few words. For this guy, in fact, it's not that strange. It's somehow, if we forget about this marking things, I mean this G, look at it as a root system. This guy is isomorphic to the BCCL4 and also isomorphic to CHECK-BCL1. So in some sense, this we have some curious things is happening here. So so just a few words. So here, if you can compute the number of the roots appearing here, you have 6 one, but all of them are known. These 4 from Kenji Saito and this from Azam Said. And here for the non-reduced case, you have 34 type appear in this part. But as I said, as a root system, this BCCL4 and a CHECK-CL2 diamond and a CHECK-BCL1 are isomorphic. So you can also imagine that there should be another isomorphic root systems, and which is the case. So if you classify by it, starting from this list, you may only get 20 new root systems, well, which still is reasonable, I may say. So now, what is interesting with this is, in fact, if you look at the automorphism groups, you may see something of the nature of the kind, what is called, why we call it elliptic. Well, so we may take any marked elliptic root system RG and look at the automorphism of R fixing radical. And also the gamma plus R, where in this radical part, in any case, we may look at the automorphism in a sense it should be isometric, then the radical should be preserved. But then we assume that the restriction is SL. So just to keep some orientation in a sense. Let me denote this odd plus R with those keeping the orientation of this radical part. Then, what one may see is this short exact sequence, which is somehow the natural one, where the this projection here, if you look at it, it's clear that it's just given by the restriction of this one, phi to this radical of I. And then the kernel is, of course, those fixing the radical, so something really natural. And you may see that it splits. Now, if you look at the projection to the other side, rather, this times to f to the f over the radical, then this induces a surjective morphism from here to there, and this also splits. So at the end, you have such structure. Here, this is classical automorphism group of the finite root systems. So it's basically those comes from the Dynkin diagram automorphism, or just the Y and the Y group, finite Y groups. Here, this is somehow the translation part of the Y group. So it can be related to the Heisenberg part in a sense, if you think of the central extension. But here we don't take the central extension, so it's just a lattice. Now this for gamma plus R, if you compute everything, I mean all of the types, you may get SL2, either SL2Z or gamma upper 02 or the lower 02, gamma upper 03 or the lower 03 or upper 04 and the lower 04. Remember that this one is the one where in the 2-1 component of the matrix is even, and this is the 1-2 component of the 2x2 matrix is even. And of course, they are all subgroups of the SL2Z, and so forth and so forth. And gamma theta is a subgroup of such kind. And it disappears. Well, just for fun, this gamma 04 and both gamma 04 appears only in the non-reduced case. And in the reduced case, this gamma 03, both gamma 03 appears only in the reduced case. And these are related to the G2 types. Otherwise, the rest, SL2Z, gamma 02, and gamma theta appears in the non-reduced or the reduced case. And you know that this gamma 04 are isomorphic to gamma 2, and this invariant is a lambda function. So thinking about the non-reduced case, as I said, this two, gamma 04 appears only in the non-reduced case, could have some interesting meaning. Of course, the SL2Z invariant is this famous J function, J capital or small, it depends on the normalization or some constant term and so forth. And this J and the lambda is related with this famous equation, as you may know. By the way, so this automorphism groups itself is determined by, I think, by two Saito. I mean this K Saito and the Y Saito with these two different characters. But it seems that K Saito knew it, or very knew it, even in the beginning of 90s. But he he never wrote such things, and it was just recently in their paper, which is still in preparation since 4 years. They're having this statement. So our results somehow about the classification relies on their fact, and it's quite complicated to handle this affair. But as Saito is one of our co-author, I mean, we got this news and we could do it. By the way, as for the motivation, where does this come from? In fact, for this, in a sense, this root system is interesting for the reduced case. In particular, if you think of the what people call simply elliptic singularities. This is a singularity, the surface singularity, which is, if I don't make mistake, normal, and in the minimal resolution, you should have the regular elliptic curve as exceptional devices. So in a sense, there are some number of the cases, I mean, for E611 and E711 and E811, which is of this kind, and this lambda is somehow related to the lambda function, or the value of the lambda functions of elliptic curve, which appears in this boundary. And these can be constructed by taking an elliptic curve with this same value of tau, and think of the line bundle of the degree -3 for E611 and -2 for E711 and -1 for E811, and contract the zero section. Then you get these singularities. Or in a D511 case, you may look at it in P3. Yeah. So you have this two surface, I mean a hypersurface, and you look at the intersection, and this gives you elliptic curves. And from that one, you look at the cone of this guys. I think, no. You just look at the intersection of these two in P3, you get the surface with the 4A1 type singularities which appear in there, which is code of type D511. Of course, it may remind you of the Riemann bilinear relations for this type of equality. So that's for the reduced case. And why it's interesting to look at this one, because if you think of the simple singularities, which is also parameterized by the root system, this time for type A, D, E. In fact, these root deformation of this simple singularities and the simultaneous resolution of these singularities are all realized in terms of AD type Lie algebras or algebraic groups or whatever you like. So history since the end of 70s was to realize similar things, probably only the same universal deformation of this one, purely in terms of Lie algebra, or the Lie theoretic things, algebraic groups or Lie algebra. In fact, for the in an algebraic group side or holomorphic Lie group side, you can think of realizing it inside the affine Lie groups, but holomorphic context, not in the C infinity on a circle. And and for the Lie algebra side, you have to look at some Lie algebra, which is of infinite dimensional, associated to these elliptic root systems. So you may look at the two toroidal Lie algebras or some version of the two toroidal Lie algebras. To be precise, you need a C-infinity completion of that one. View the polynomial part as a finite Fourier series in a sense. So already the structure of itself, if you look algebraically, it appears that it may not be so simple to get these singularities, because in some sense you need some analytic completions and you have to put in analytic context. And this is a huge abstraction, and right at the moment we have no idea how to go further in this direction. But the original motivation was to write down in a theoretic way to compute the period maps, which is of where you can expect to have some sort of, say, interesting functions. For the complete intersection case, it's still not quite clear how to realize it, even at the Lie group side. So this, we don't know. We really know nothing. Now, for the non-reduced case, as I evoked a little bit in the reduced case, this period map like things gives you some sort of, say, special value of the hypergeometric functions, or some special case you can compute with hypergeometric function of Gauss. So what we suspect is that in fact, in the non-reduced case, maybe we can find some new special functions, which is of course good, if possible. We don't know. But being optimistic, we somehow believe that this is the case. To be a little bit more precise, we may think of the orthogonal polynomial type things. I mean, for the one variable case, you have this Askew-Wilson polynomial, which is, say, the most generic in a sense of Leonard, which says that if you have this three-term recursion relations of this polynomial, and with some conditions, it's essentially Askew-Wilson polynomial, which gives you the answer for the realization. So you can't find anything more, I mean, more general things. Now for the multivariable case, already the notion of the orthogonal polynomials are quite well. Of course, if you think of some weight functions, and you can define the orthogonality and so forth and so forth, you can define it, but there still is not that general theory as in a one variable case. So many things are mysterious. Here we have this generalization of the Askew-Wilson polynomial to the multivariable case, which is called MacDonald-Cohn-Windner polynomial. But the question is this generic, as in the case of one variable? Well, nothing is guaranteed. We believe or expect that this may not be the general case. The reason why we think that is it's somehow related to, if you wish, this Daha-like business. I mean, this double affine Hecke algebra type business of the Tredenik. And MacDonald-Cohn-Windner polynomials are somehow related to the CL, the pair of CL and the CL check case. If we look at it in terms of the affine root systems. And the number of the parameters there is 5 or 6, which I can't remember. But we have a root systems we found which might be related to some polynomial with the 9 parameters. So this is something we hope having something new, but still we don't know how to handle it. So this is something, the double affine Hecke algebra is somehow related to the elliptic root systems, and known case like the McDonald polynomials are related to, say, elliptic root systems with a reduced quotient. So if we go to the Cohn-Windner polynomial, which is related to the type BCL type case, then it would be related to this non-reduced elliptic root systems with a non-reduced quotient. So we somehow expect having something in relation with our root systems to have a more general one, which is not clear, but this is something we expect. The other one, if you know of it, well, I imagine that you already heard of it. Selberg wrote one very interesting paper, which is called Remarks on the Multiple Integral. And this journal, this Norsk Mat something which I can't read, appears in the Norwegian journal, which is aimed for the high school teachers. Well, it's quite amazing that he submits this paper to such journal, believing that this is already well known and the technique or the something like this integrals are very simple. I will show you. So it talks about such integrals for p, the number of the variables, and x, y, z, a complex number with some technical conditions, I mean the convergence at the boundary. You evaluate this quantity. Well, you can write it in gamma factors. And he wrote such paper to this journal for high school teachers. Well, if our high school teachers understand this one, I think there are less problems at the faculty right now, and this is fairly unimaginable. But the point is that here in this integral, coming back to our story, there are several generalizations of such kind of integrals, in particular in relation to the BCL type root systems. For the elliptic case, there is an elliptic generalization due to Sedanov, I suppose, and several others are also involved in this kind of business, but there still is not a work on a generalization related to our root systems, because our paper is also in preparation already for 1 year at least, and it's about 110 pages long, and it's still we imagine that we can have 40 pages more. I don't know. So of course it's natural that there still is not that generalization related to our root system, since we don't work on that one yet. If possible, we would like to think about it. And there might be another kind of, say, generalization in relation with our root systems, and which is of interest. So this is nearly all what I want to present. And thank you very much for your attention. So it's finished.
Thank you for your talk. Are there any questions? No question. I think we can stop recording at this point.